modes up there. All right, so we're going to start with brems spectrum and the effects of technique on brems spectrum, and then when we run through everything that affects brems spectrum, we'll take a look at PowerPoints. But I want to draw it out and kind of review what we talked about last semester. If you can kind of do the legwork and understand what it is that we've got going on with brems spectrum and how how different technical factors and different equipment factors affect the brems spectrum, it'll make chapter 13 a lot easier for you. And then whenever we get into chapter 10 and the effects on the image itself, it'll also make that easier. It'll also make it a little bit easier in Rad to better understand the effects of radiation dose to the patient with technical factors. So when we're talking about the brems spectrum, what we're talking about, again, we've got two different ways to create X-rays. We've got characteristic and we've got brems. And most of the X-ray photons, if you remember from last semester, statistically they say 85% of our X-ray beam is brems and 15% are characteristic. So most of the X-rays we expose the patient with, and most of the X-rays that strike the image receptor are going to be created by brems, which is just slowing down of the electrons and creation of photons relative to the amount of energy lost in that slowing. So in the brems spectrum, what we've got are photons that are created with the minimum energy all the way to the maximum energy. Remember, 69 and a half technically is your characteristic spectrum that we recognize. So all of the other photons that you create are brems, right? So if we were to take and draw out a brems spectrum as it leaves the target itself, then what we're going to have, if this two-dimensional chart represented the energy level in kVp, so that's kVp, and the number of photons that we create. And I'm going to refrain from using mass as the numbers because a lot of different things affect numbers as they exit the X-ray tube. So we're just going to say numbers and energy level in kVp. All right. So if we were to take and chart the number of X-ray photons at the energy level that we're creating, then what our brems spectrum at the target would look like is this. Okay? Because when we talked about X-ray creation last semester, we said that the likelihood of an X-ray being created is high or low? Low, very low. Right, and then the likelihood that the electron is going to pass close enough to the nucleus of the atom to create high energy X-rays is likewise very low, right? So most of the X-rays, the highest number of X-rays that we create are going to be very, very low energy. The number of X-rays that we create that are going to be high energy are going to be very low, okay? So as it leaves the target itself, that's what your brems spectrum is going to look like. But we don't expose the patient to the X-ray beam just as it leaves the patient, right? We expose the patient to the X-ray, as it leaves the target. We expose the patient to the X-ray beam as it leaves the collimator housing, or you should be anyway. So what does it have to pass through to get through the collimator housing? What's the first thing it's going to hit? The glass or the metal envelope, right? So we say that we have two different types of material. We've got radiopaque and then we've got radiolucent, right? What does radiolucent mean? What's that? It goes through, but it still absorbs some. So when we look at this, we can say, well, we've got all these numbers that are very low energy, but as it passes through that glass or metal envelope, then something's going to happen. Some of that's going to be absorbed. So what we know about X-rays, what we think we know about X-rays anyway, is high energy X-rays are going to pass through things a whole lot easier than low energy X-ray photons, right? So what's going to happen is as it goes through that tube housing the high energy photons should remain unaffected. So that as it goes through the tube housing, it's going to take out some of those low energy photons, so our brems spectrum, as it goes through, looks like that. As it goes through the tube housing, looks like that, okay? So that's housing. What's the next thing it goes through? What's that? The oil, right. So what's the purpose for the oil? Yeah, to dissipate heat. So what is oil? What is it?
An insulator.
It's a liquid, right? It's a liquid very similar to water. It's a little bit lighter than water. So what are you made of? Water and, we hate to admit it, but fat, which is just solidified oil, right? And with some water mixed in with it. So do you absorb X-rays? Absolutely. If you didn't, then there would be no point in exposing you to an X-ray beam because we wouldn't get an image, right? So do you absorb X-rays? Yes, you do. So will the oil absorb X-rays? Yes. The answer is yes. So it goes to the oil and it takes more of those low energy photons out. And again, the theory behind X-ray behavior is that the high energy photons should be unaffected. They should pass right through. All right. So we got oil, and then we've got the housing. What's the next thing that it goes through? What holds the oil in? Or I'm sorry, that was the X-ray tube. I kind of gave that away.
Yes.
Yeah. The tube, the oil, we'll say envelope. Okay, so now it's the housing. So the housing holds the oil in, and it's, if you remember, we've got two different reasons for the housing. One is to protect the tube from you, and one is to protect you from the tube, right? So it limits the amount of leakage radiation or radiation outside of the collimated area, but it's going to be made of metal as well. So metal, you ever taken an X-ray on a patient that you forgot to lower their blue jeans? If you haven't, you will. Or you get a patient from the ER and you think that they're dressed for X-ray and you find out that they're not because they got a zipper or something. So metal absorbs X-rays, right? So again, we're going to lose some X-ray photons. All right, so that's the housing. So what now? What does it go through now? You turn the light on and you look up into your, even without turning the light on, you look up into your collimator housing. What do you see? A mirror, right? So why do we not just shoot straight through a light? The light represents a radiation field. Why do we not just shoot straight through the light? The light bulb will cast an artifact. So that's one reason. Really, the other reason, there's really two. One is that we've got to have the same distance from the focus to the patient as what we have from the light bulb to the patient. So really what we would have to have is the light bulb directly on the focal tract. And that's just never going to happen. So what we see is a mirror. And what is a mirror made out of? And probably some sort of metal on the back side of it to make it shiny and reflective, right? So it goes through the mirror, and finally it looks like that. Okay? So what you expose the patient to is a highly filtered, relatively highly filtered anyway, X-ray beam that is removes a lot of the low energy X-ray photons. Now, if you remember back to first semester, we talked about Bill Rollins, and he was the dentist, and he invented two things. And both of them were to reduce radiation exposure to the patient. What were they? Collimation, beam restriction, and filtration. Right, so filtration is what he did, and that's what all this stuff does. Is that the purpose for all that stuff? Well, not really. Tube envelope, you gotta have it. This is a vacuum tube. The oil is to keep the tube cooler so that you don't burn your tube up real quick. The housing is to hold the oil in and reduce dose to you as well. And the mirror is to reflect the light. But all that provides filtration. The purpose for all that is not filtration, but it provides filtration. So in a diagnostic x-ray tube, you have to have 2.5 millimeters of aluminum equivalent if you're operating above 70 kVp. Okay? So if you're operating above 70 kVp. 70, or better still, 70 kVp or above. All right? So all of your diagnostic tubes are going to be set up with that. If all this only gets us to 1.5 millimeters of aluminum, then what do we need? More. We need more. Because legally we have to get to this point before we can make the exposure on a patient. So we have to get to 2.5 millimeters of aluminum, and therefore our brim spectrum becomes more and more filtered so that our brim spectrum takes on this elongated bell curve appearance as opposed to that just not really a straight line, that slope that we had before, okay? So we're going to start with filtration in things that affect the brim spectrum. So all of this was filtration. If we added more filtration to this, what do you suppose would happen? You've seen the progression. It went from peak here to peak here to peak here to peak here. If we added more filtration, what logically do you think would happen? The peak would be lower. Exactly. The peak would be lower. So what we would have is if we added more filtration, then our peak would be lower. Now, what does the peak really represent? What does the height of this bubble really represent? Numbers. It's just numbers. So the peak energy is represented by the right-hand side over here, okay? So we'll go back to our original brim spectrum, and it looked like that. And if we have so many low-energy photons that most of what we create are low-energy photons, then our average beam energy is going to be extremely low, okay? So by getting rid of a whole bunch of these low-energy photons, what happens to our average beam energy? It increases. What happens to our numbers? It decreases, right? So filtration increases the average, and it's not because you get an increase in anything, really, but it's because you got a decrease in low-energy photons. So I think I used this analogy last semester. I use it again this semester. If you have, say, 7 test grades and you tank 2 tests, I mean, you really messed up 2 tests. What does your average look like? Not good, right? We don't have to throw a number at it. You know that if you really messed up 2 tests, your average is going to be very poor. Now, if I threw out those 2 tests, what would your average do? It would go up, not because you did better on other tests, but because I got rid of those low score tests, right? So that's what happens with filtration. You lose numbers and you increase your average, your numbers go down, decrease numbers. What else changes? So back to the test analogy, let's say you had, let's go with 5 tests. And on those 5 tests, you scored a 50, a 60, a 70, a 80, and a 90. Okay? So if I threw out the lowest test grade, what would now be your, was the 50, what would now be your lowest test grade? 60, right? So the minimum increases, right? Same thing with filtration. What was our minimum effective energy level of an X-ray photon with no filtration at all? Effectively 0, right? It was the lowest possible energy level you could get, right? So the upper end didn't change. The lower end changed by removing those low energy X-ray photons. So it increases the energy level of the lowest, not increases the number, but increases the energy level of the lowest X-ray photon. So drawing this more accurately, it looks something like that. So that before your lowest energy was effectively 0, now maybe your lowest energy is effectively 5 kVp. Okay? So if we increase filtration, keep increasing filtration, what happens is that number goes that way. This average goes that way towards the high energy side, and our numbers continue to decrease. Okay? So if I continue to add filtration, would that come with radiation safety implications for the patient?
Yes.
Absolutely, absolutely. Increased filtration, you're gonna continue to decrease patient dose. Is that gonna come with implications for image receptor exposure?
Yes.
Absolutely, right. So even though these are low energy X-ray photons, might there be a possibility that they would reach the energy, to reach the image receptors? Answer is yes. So if they possibly could reach the image receptor, they change the image receptor exposure, and by virtue of removing those, your image receptor exposure is going to go down with increased filtration. Okay? So bringing technique into it, what would you have to do if you shot the perfect X-ray with a minimally filtered X-ray beam, and then you increase your filtration? What would you have to do to compensate for that increased filtration? You'd have to increase something, right? Most of the time, whenever we make changes to the intensity of the X-ray beam, be it through filtration or grids, use of grids, pathologies, almost every time that we have to do a technique compensation, lock into your mind that unless you need to increase or decrease the penetration through the patient, you're going to change mass, okay? I expect in your career, as they dial in the imaging and the image manipulation of digital and computer radiography, that might change to kVp. But for now, the testable the patent answer on the registry is going to be almost any time that you make a technique change, it's going to be a mass change. Okay? So just cement that in for now. Again, unless you need to change the absorption characteristic of the X-ray beam, which would be kVp. So filtration. All right. So I don't know, pick a technical factor. What do you want to do next? kVp, okay, kVp. So we've got unfiltered, we did that, right? And this represents peak energy, right? So if, let's say, our original technique over here, it doesn't really matter what the mass is right now since we're going with kVp, if our original technique, our kVp was, let's say, 60 kVp, and we used however much filtration to arrive at this. If we removed all the filtration and changed our peak energy, then where would this line intersect? Should hit down there like that, but drawing's not perfect. Okay, so where should it intersect just in general? To the right, right? So if I were to change nothing but my kVp, or remove filtration and change nothing but the kVp, then what I'm going to do is my spectrum should fairly parallel that one. It's going to start higher. I'm going to create more X-rays. Most of those X-rays are going to be low energy photons, right? For the same reasons they were low energy photons before, but I'm going to get more of them, okay? Now I introduce all this filtration, and what I'm going to have is the spectrum, the comparative spectrum, is going to look like that, okay? So I increased my kVp. Originally it looked something more like that, all right? So what the peak, the very height of that bubble represents is the average, okay? So as we increase kVp, we increase the peak. Let's say I went from 60 kVp to 70 kVp. Okay, so this was 60, that was 70. So what happened to the peak? Well, peak increased, right? But what happened to the average? It went up too, right? So back to the test analogy, you've got 5 tests, right? You got a 50, a 60, a 70, a 80, and a 90, right? So we eliminated the 50, what happened to your average? It went up. Now I gave you another test, still threw that one away, but I gave you another test and you aced it. You scored 100 on it. What happens to your average? It goes up, right? So as we increase kVp, our average goes up, right? So the height of the bubble increases because I've got more numbers. But the bubble, the peak of the bubble itself pushes to the high energy side, giving us a higher average. Okay, so kVp, we increase peak, we increase average, we increase numbers. The only thing that we don't increase is the, I'm going to get rid of these right now. The only thing that we don't increase is the minimum. The only thing that affects the minimum energy is filtration, right? Now, the only thing that affects the maximum energy is kVp, right? It's kVp, kilovoltage peak. So the only thing that affects it is going to be your kVp. So we increase peak energy, we increase average, we increase the numbers. There's one other thing though. Well, yeah, mass we're going to get to, I mean, is in relationship to kVp. What's that? Low energy was only affected by your filtration. You're going to go, here in a minute.
What was the question?
There's one other thing that kVp will affect. We went from 60, here's your hint, we went from 60 kVp to 70 kVp. What do we now have that we didn't have at 60? What's that? Bingo, characteristic. kVp controls whether or not we have characteristic spike. And characteristic spike is going to be represented on the brems spectrum just as a spike. Okay, so we're at 70 kVp. We've got characteristic. So, and characteristic is going to be at 69, 69 and a half. So if we set our control panel, we set our kVp. When we set our kVp, we set the contacts on the secondary side of the auto transformer, right? And if we set our kVp at 69 kVp, characteristic starts at 69 and a half, right? So if and just to make it easier, let's say 68 kVp. And my auto transformer works properly, and my potential difference across the tube is actually 68 kVp, am I going to have a characteristic spike? No, I won't. Will I have characteristic X-rays? Yeah, and all those other shells that we don't, we don't recognize, but I'm not going to have a characteristic spectrum as drawn on a brems spectrum. So if you're ever looking at two characteristic spectra, and one looks like this, and then the other one looks like this, what can you say about those two?
The bottom one is higher.
The bottom one is higher, and it specifically is above
69.
69 kVp, right? The other one is too low to get to characteristic spectrum. Okay? So kVp, the only thing that it does not affect is minimum energy, because the only thing that affects minimum energy is filtration. The only thing that affects maximum energy is kVp. Right? Okay, so now we're going to get to mass. Okay? So we're going to do MA and time together because it doesn't really matter how you arrive at your mass. Certainly in setting your techniques, MA and time separately do matter because you can introduce motion with too much time, or you can introduce quantum model with not enough time. But in as much as what we're talking about here, they're just together. All right, so if I take an X-ray, I'm not gonna draw it all the way back out to the unfiltered. If I take an X-ray at, I don't know, we'll say 50 mass. Okay, so we got 50 mass. What does this over here represent? Numbers, and this represents peak energy, right? So energy level, that's your peak, and those are your numbers. So I got 50 mass. If I were to increase, well, first off, what do we refer to mass as being? Numbers or quantity or intensity, right? So all three of those things represent our mass. So this is our, let me make sure so that you can see that on the, take that out so that it's not confusing if you look at it later. This is filtration, and this is mass changes. Okay? So we've already established that only one thing is going to affect where the line on our brim spectrum hits this line, and that is going to be your, right. We've already established that the only thing that's going to affect where it takes off from this end is your filtration, right? So what's left? And we already established the only thing that affects whether or not you're going to have a characteristic spectrum is also kVp. So what's left? It's just the height, right? Just the height. So what we've got in mass is we should have a brim spectrum that you can't really say it parallels. You know, if we increase our mass, you can't really say it parallels because it intersects, and it bubbles out in the middle. So average, no change. Peak, no change. Minimum, no change. Mass is only about numbers, right? So it increases the height of the bubble. That's the only thing that it affects, nothing else, okay? So we got filtration, kVp, mass, and really the only other thing that we have is generator type. So generator type. So we got two different spectra for generator type. And say we shot with a technique, a specific technique. You plug in your numbers. Doesn't really matter what the numbers are. We said that minimum is only controlled by filtration. Maximum is only controlled by kVp. The height is controlled primarily with mass, but we've seen that everything controls numbers, right? Same thing here. So we go from a single phase, we'll say this is a single phase, to a three phase, and two things are going to happen. Nothing's going to happen on the minimum end, nothing's going to happen on the maximum end, but everything else changes. All right, so it takes off from the same spot. If we go with a three phase or a high frequency, that was more of a mass drawing. It's subtle, the difference between generator type and mass is subtle, but the differences remain. Okay, so we've got a single phase and we've got a three phase. Now, it's going to require some thinking. Last semester we said that whenever we changed our from single phase to three phase, what never happened? The pulses never did what? Never dropped to zero, right? So again, back to your test analogy. You miss a test and you never make it up. What's your average? Low, right? Throw that test out because you had a zero. We got rid of that zero. What happens to your average? It goes up. So what does the peak of the bubble represent? Not only numbers, but also the position of the peak of the bubble. If it's more towards the high energy side, that represents a higher average, right? So the height of that bubble, you know, we're looking at the three phase, I missed it, here, as opposed to here. So what happened to the height, the very peak of the height of that bubble? It pushed more towards the high energy side, right? So you go from single phase to three phase, or single phase to high frequency, it pushes towards the high energy side, but it doesn't do anything to peak. Why? Because kVp is the only thing that affects peak, right? Doesn't do anything to minimum. Why? Filtration is the only thing that affects minimum. But it does increase the average. It increases the average and it increases the numbers. Okay? So we get an increase in the numbers and we get a push of average towards the high energy side of the spectrum. All right. Now, here's where you're going to kind of struggle with all this. Is that with filtration, what do we get? Increase in average. With kVp, what'd you get? Higher average. With generator top, what'd you get? Higher average, right? So it increases the average and it increases the number. Right, so what you're gonna struggle with is you're gonna take a look at filtration, you're gonna say, well, filtration, kVp, generator, all increase the average, and then you're gonna kind of draw a parallel with numbers. The average, yeah, they're all the same. They increase the average. But with the numbers, what we get is with kVp, we get an exponential change in numbers, right? With generator top, we do get an increase in numbers, but it's not exponential. And then with filtration, what happens to our numbers? They decrease. Right. Right. Okay. So that's the brems spectrum in roughly 30 minutes. Again, you know, kind of do the legwork and kind of run through this over and over in your mind, and it will help in your chapter 13 studies and chapter 10 studies, because running back through it, if kVp, increasing kVp does all this stuff, and that's the only thing that you change is kVp, then what's going to happen to your patient exposure? It's going to go up, right? And what's going to happen to your image receptor exposure? It's going to go up, right? So you got all this over here with mass. What's going to happen to your, and it's the only thing that you change, you increase your mass. What's going to happen to your patient exposure? It's going to go up. What's going to happen to your image receptor exposure? It's going to go up, right? You change from single phase to three phase. What's going to happen to your image receptor exposure? It's going to go up. What's going to happen to your patient exposure? It's going to go up, right? So if you shot the perfect X-ray with 2.5 millimeters of aluminum and you changed your aluminum to 3.5 millimeters of aluminum, you had the perfect X-ray, what are you going to have to do? Change mass, right? So change mass. Okay, so now you got you've got a perfect technique for a patient, right? And you find out the patient's pregnant, but they have to have the X-ray. They have to have the X-ray, right? So, you know, maybe they're a trauma patient and they've got severe back pain, and we need to see if they've, you know, something's going on. So we have to take a KUB or an L spine on the patient. So what do you know about kVp and patient dose? As kVp goes up and mass goes down, what happens to patient dose? It goes down, right? So how do you manipulate this for a pregnant patient? Well, you would increase your kVp, but because you increase your kVp, you increase all this stuff, you can reduce your mass and lower the patient dose as opposed to, you know, your regular technique, right? So let's say you've got a patient and you're doing a portable chest X-ray, or let's say a portable KUB on a patient. How do you manipulate your MA and your time on a portable machine most of the time? They're together, right? It's a mass timer. You remember talking about the different types of timer? A mass timer means you've got a set MA and you're actually selecting your exposure time to select your mass, right? So you're shooting a KUB on a patient who can't be still. What's the main thing that's going to destroy your sharpness of reported detail? Motion, right? So how do you reduce your motion while doing portable? Reduce the mass, the overall mass. Well, how could you reduce the overall mass? Now, you can't reduce time because you're working on a portable. And if you just reduce your overall mass, then what's gonna happen to your patient exposure, your image receptor exposure? It's gonna go down, right? Possibly to the point that you don't get a diagnostic x-ray. So what are you gonna have to do? Decrease mass and increase kVp, right? So you're probably in your career never gonna see this. I've been unfortunate enough to work in a hospital that in the ER of all places, we had a single phase room right next to a high frequency room. Nightmare scenario. Because the techniques are so greatly different. One was phototimed, and even though it was a high frequency room phototimed, it was a doctor's office type machine that they scrimped and put it in the ER. The other room was unphototimed single phase room, okay? So if you were shooting and you knew a technique for one room, then you had to convert it to go into the opposite room. So you shoot a kUb in a three-phase room, and you should start now looking at the technique whenever it shoots. You know, you make your exposure on the patient, look down at the control panel and see what mass you got. Start making mental notes and start making a mental technique chart for, for set techniques for patients. Okay, so you shoot in a phototime room, three-phase room, and it gives you a technique of, I don't know, you shot a kUb at 80 kVp, and it gave you maybe 30 mass. Okay? But now your machine broke. So you got to take them into a single phase room. What is your technique compensation or your technique change for a single phase, three phase, single phase? Factor of 2, right? So you went from a three phase that had this output and that average to a single phase which had that output and that average. What's your new technique? You have to multiply it by 2, which tells me you didn't hear my technique to begin with. 30. So now your new mass is 60. Yeah. Okay? So understand your brim spectrum and what is, I was busting on you. But understand what's going on when you change your technique and what's happening with emission from the x-ray tube. And that's what we're looking at here, is not emission from the target, but emission from the x-ray tube. Understand those things, and it'll help you to kind of muddle your way through chapters 13, chapters 10. Chapter 11, not so much. That's more geometric factors, but those 2 chapters will help some anyway. Okay? Any questions? All right, well, we've got about 10 minutes left, so we'll get a few slides in. That's what we're doing. We're just, all right. So that's where we left off on Wednesday. So the things we'll discuss this semester regarding kVp is the effect of kVp on beam quality. I can make that larger. On beam quality and that effect on patient exposure, image receptor exposure, technique adjustment. I got too many knobs. I don't want to focus. There we go. All right, effect of changing kVp on beam quality. Effects of changing kVp on beam quality. Okay, so the effects of changing kVp on differential absorption inside of the patient. Certainly the effects of changing kVp on, okay, that's just quantity and quality.
Yeah,
Okay.
I was about to say.
Yeah. ADD and a little bit of dyslexia and you know, things get kind of muddled in my reading. All right, so the effects of changing kVp on differential absorption inside of the patient. Certainly the effects of kVp and the emission, the changing emission from the X-ray tube. The effects of changing kVp on Compton scatter and photoelectric interaction. The effects of changing kVp on patient exposure, image receptor exposure, and the overall image as we display the image. And really the theory, because again, with digital imaging now, the effects of kVp are not as drastic as what they were back when we used film. And I think the literature will change over time to reflect that. It still says on the registry kVp affects your contrast on your image, and you know, play with your machine, shooting different things in a room, and you'll see that a lot of what we talk about just doesn't really hold true. It still holds true in the physics of the interaction, but not so much in the image creation. Our digital manipulation of the image is changed to a point where kVp really doesn't affect your contrast that much anymore. Even a 15% change in kVp, your images will almost be identical. So we'll also talk about how to manipulate kVp to reduce patient exposure. We kind of ran through that a second ago. How to manipulate kVp to change image receptor exposure, which is not always the same. You know, you can do a lot of things to change image receptor exposure that to maintain image receptor exposure that might increase or decrease patient exposure. So they're not always the same thing. How to manipulate kVp to reduce patient motion, and we'll kind of walk through that a moment ago. How to change kVp to change the characteristics of the image, what effect kVp has on occupational exposure, and that is really what changes your occupational exposure, because where are you receiving your occupational exposure? What kind of photons hit you? Scatter, right? Unless you're standing right in the path of the X-ray beam, you shouldn't be hit by anything except for scatter radiation. So what creates more scatter? High kVp or low kVp? High kVp, right? So that's where you get your occupational exposure. And what other equipment is essential for changes in kVp and to deal with some of the scatter radiation. So that's just what we'll walk through right there. As we increase kVp, we increase the output from the X-ray tube. So the height of our brems spectrum goes up, but it pushes it towards the high energy side. It increases the peak energy. The characteristic spectrum doesn't move. Provided you've got a characteristic spectrum, it's always going to be at 69 kVp. If either one of these stopped right there, then we just wouldn't have a characteristic spectrum at all. So it increases the height, it increases the numbers, it increases the average, it increases the peak. Everything increases except for the energy level of the lowest energy X-ray photons, and that is from filtration. So at the console, we control mass. So remember, we've got parallel circuits. We've got our high voltage section, and then we've got our low voltage section. And really, we could break down into three. We've got low voltage, high voltage, and we've got filament, right? So everything past the step-up transformer is high voltage section. Everything up to the high voltage section, to the step-up transformer, is going to be our low voltage section, and then our filament section is going to be, the separate section, really. So our MA circuit controls the current and the heating of the filament. Remember, we don't have mass until we make an exposure, right? So when you rotor up, do you have MA? Absolutely you do. You're heating the filament up and you're getting ready to make exposure. Okay, before you make exposure, do you have mass? And that's a no. You don't have mass until those electrons are actually traveling across the tube, right? So MA is going to control the heating of the filament. The higher your MA, the hotter the filament gets and gets prepared to send electrons across the tube. So it controls the current and the heating of the filament. Again, you don't have tube current until you hit mass, until you apply the high voltage and you've got the travel of electrons across the tube. So it's found in the low voltage circuit or filament circuit, which is a separate circuit that comes off of the auto transformer. Remember in your all those drawings I made last semester, the first thing that you actually get to is the line voltage compensator, and then it goes into the auto transformer. Auto transformer gives birth to the entire filament circuit. So it works off a low voltage, and in this case, we're not talking about the 110 to the 220 that is supplied to the imaging system. What we're talking about here is that your filament circuit is actually like 25, very low, very low voltage. So the step-down transformer decreases it from anywhere from 10 to 15. Maximum would be 25 volts, not kilovolts, volts. So very low voltage, and the purpose for that is so that you don't send electrons across the tube before you're ready for them to go across the tube, right? So here's a question for you from last semester: is when do you have current through the filament? It's always present. Why? Keep it warm. Exactly, to keep it warm. Now, we don't get to thermionic emissions until we prep, right? It's just a very low current to keep it a little bit warm so that whenever you come in and you make your first exposure of the day, you're not putting a high heat load on a cold target through a cold filament. It just keeps it a little bit warm so that whenever you rotor up, you don't change that heat from very cold or relatively cold to very hot in a big hurry, because if you did, then what might happen? Crack. Burn out the filament, crack the anode, and then you've got a tube that's totally useless, right? So it's always present. You got current going through it all the time, but you don't get to thermionic emissions until you prep. It just is not that hot until you hit the prep stage. So your MA selector just uses precision resistors, and we really kind of beat the auto transformer in last semester as being a rheostat, but really this is a rheostat as well. Your MA selector is just a series of resistors that dial in specific MAs, and it's just a rheostat as well. So time selection occurs in a separate circuit. If you remember, the way I drew it, you had line voltage compensation, and then you had auto transformer, and then you had that going into the high voltage transformer, and then the timer circuit, if you remember, was up in the low voltage side, just kind of up in between the auto transformer and the high voltage transformer. You remember seeing that? So time selection occurs in a separate circuit. Calculation of mass is just MA times time. The mass, again, we refer to as quantity or intensity, just the numbers. And the MA meter, though, is the only meter in the high voltage circuit. And if you remember, it was wired into the secondary side of the step-up transformer, and the reason it was wired in there was that if it's right dead square in the middle of that, the voltage always remains at 0. So it's in the high voltage section, but it still works off a low voltage. You remember the test question that it was a two-part question. All Gauges are found in the secondary side, well, no, the primary side of the circuit, secondary side of the auto transformer, and work off a low voltage. Well, that's a two-part thing. Well, they all work off low voltage, yes, but are they all in the secondary side of the auto transformer? The answer was no. You had that one MA meter that was on the secondary side of the step-up transformer. So mass, what does it control? It controls the number of electrons we send across the tube. It controls the thermodynamic emissions on the filament. And since it controls the number of electrons, it controls the number of X-rays we create. So therein, it also controls directly the number of X-rays emitted from the tube. Now, is it the only thing that affects the number of X-rays we create? No, we just walked through that. Everything affects the number of X-rays we create. So increased mass techniques increase two things. Heat is unintended, so we have to deal with that because it shortens tube life. That's why we have the rotating anode. That's why we have the fan system, and it may just be a bellows system inside of the tube housing, right? Or we can change the amount of oil in the tube housing to lengthen that life, but heat is the main thing that kills the X-ray tube. And it increases the current, increases the mass, increases the current, and that's what we want. Whenever we're making a technique adjustment, if we increase mass, we get a change in heat. We don't want that. What we want is a change in the numbers of X-rays we create. So changes in mass are directly proportional to emission. Increases in mass causes an equal increase in emission. That means if you double your mass, you double the number of photons that you emit from the X-ray tube, right? It's a direct relationship. Increases in mass cause an equal increase in patient exposure. You double your mass, you double the patient exposure. And it also causes an equal increase in image receptor exposure. You double your mass, you double the exposure to the image receptor. So it's a one-to-one relationship between numbers and mass. And for that reason, we use mass as technique compensation most of the time. It's predictable. You don't change the imaging characteristics of the X-ray beam, nothing changes except for numbers. And that's why, you know, the patent answer for inadequate exposure is always going to be changes in mass, right? So, we're really out of time. I wanted to finish up mass, but we're really out of time. Trina will be down here in just a second. Any questions? Okay, so the 20th, actually, I mentioned that we were going to cover positioning next Wednesday and Friday. And Trina's going to give us her class on the 20th, so we're just going to do it one day instead of all week next week.